Welcome to the University of Waterloo's Mechatronics Engineering Information Session. If you're curious about robotics, automation, or smart systems, you're in the right place. My name is Abby, and I'm the undergraduate recruitment specialist for the Faculty of Engineering at Waterloo. In this session, I'll give you a quick overview of our Mechatronics Engineering program, including what you'll study, the kinds of hands-on experiences you can expect, the co-op opportunities available, and where this degree can take you after graduation. So, what exactly is mechatronics engineering? Mechatronics is a multidisciplinary field that brings together mechanical, electrical, and software engineering to design smart, automated systems. If you're interested in robotics, autonomous vehicles, wearable tech, or intelligent manufacturing, this program is designed to take you there. A simple way to think about it is we make machines smarter. Mechatronics engineers don't just build devices, they integrate hardware and software so that systems can sense, think, and act. It's this combination that powers everything from self-driving cars to surgical robots to smart home devices. Waterloo's Mechanical and Mechatronics Engineering Department is the largest of its kind in Canada, with 68 full-time professors and expertise across a wide range of exciting fields. For example, we have leading research in additive manufacturing, autonomous vehicles, green energy, and assistive technologies like exoskeletons. Our RoboHub is a unique multi-robot facility, one of the only ones in the world to bring together ground, aerial, humanoid, and magnetic levitation platforms under one roof. From advanced robotics to micro-electromechanical machines, the work happening here is pushing the boundaries of what's possible. The Mechanical and Mechatronics Engineering Department at the University of Waterloo is committed to fostering a positive and supportive learning environment. One unique feature of the program is its cohort system, where students take courses with the same group of approximately 90 to 120 classmates throughout the entire degree. Cohorts typically remain in the same classroom for lectures during the day, helping to build strong connections and a close-knit academic community. Hands-on learning is embedded throughout the curriculum. In first year, students participate in the Engineering Ideas Clinic, where they begin developing practical engineering skills through structured design challenges, prototyping exercises, and experimentation. As students progress throughout the program, they gain experience with machining, measurement tools, control systems, and lab-based investigations across areas like thermodynamics, fluid mechanics, materials, and manufacturing processes. In upper years, students take on more complex design projects, including their capstone design project in their final year. These projects are student-driven and often involve designing, building, and testing physical prototypes to solve real-world problems. Beyond the classroom, students can also join extracurricular design teams where they apply their skills in competitive collaborative environments, designing everything from solar cars and rockets to autonomous underwater vehicles and robotic systems. From the very beginning of the program, students in mechatronics engineering are engaged in hands-on learning. In MTE 100, the introductory course taken in first year, students begin designing, building, and testing real devices. The course challenges students to solve open-ended problems, such as creating machines that can sort balls by color and weight, or programming and assembling mobile robots that can navigate a course and interact with their environment. These projects require that students apply their growing knowledge of mechanical systems, electronics, and programming in a collaborative team-based setting. It's a great example of how students start developing practical engineering skills early on, while also learning how to prototype, test, and iterate like a real engineer. In fourth year, all engineering students participate in a capstone design project. Working in teams, students identify a real-world problem and design a solution to address that need, applying everything they've learned throughout their degree. This work culminates in the design symposia, where students publicly present and demonstrate their projects to classmates, faculty, industry partners, and community members. Projects span a wide range of industries and challenges. Past examples include robotic hockey stick testers, drone applications for package delivery, automated greenhouse systems, and assistive technologies for individuals with vision impairments. These projects are an opportunity to showcase not just technical and design skills, but also communication, creativity, and teamwork. For many students, it's one of the most rewarding and memorable experiences of the program. So let's get into what you'll learn in the mechatronics engineering program. In the first year, students build a strong foundation across several core subject areas that support the multidisciplinary nature of the field. Courses in mathematics and science include calculus, linear algebra, and chemistry, which provide the analytical tools needed for engineering problem solving. In the Introduction to Mechatronics Engineering course, students are introduced to engineering design, control logic, CAD, sensors, actuators, and basic project planning, giving them early exposure to mechatronic systems. Students also take courses in computing and digital systems where they learn basic programming, algorithms, and digital computation, skills essential for automation and software control. In mechanics and materials, students explore statics and material properties, learning how mechanical components behave under different conditions. Finally, in electrical circuits, students study the fundamentals of circuit analysis and electronic components, such as resistors, diodes, and transistors. Altogether, this first year equips students with the foundational knowledge they need to dive into more advanced and integrated topics in later years. So let's explore the four core areas of mechatronics engineering, starting with mechanical engineering fundamentals. This area lays the groundwork for understanding how physical systems behave, which is essential when designing and integrating mechanical components into smart automated systems. Students begin with statics and dynamics, learning how to analyze forces on stationary items and how objects move under various forces. These concepts are foundational for designing reliable mechanisms in robotics and machines. Next is mechanics of deformable solids, where students study how materials respond to stress, strain, bending, and torsion. This helps in designing components like shafts, brackets, and support structures that are safe and efficient. Courses also include fluid mechanics, which explores how liquids and gases move, which is important for systems involving pneumatics, hydraulics, or cooling. Finally, thermodynamics and heat transfer help students understand how energy and heat move through systems. These principles are crucial for energy efficiency and thermal management in devices like motors, processors, or power electronics. Altogether, mechanical engineering fundamentals give students the essential tools to design and analyze the physical side of mechatronic systems. The second core area in mechatronics engineering is electrical and electronic engineering. This area gives students the tools to design and integrate electrical systems into mechanical devices, making systems smart, responsive, and automated. Students start by learning circuit analysis and electronics, including voltage, current, resistors, capacitors, and transistors. These concepts are the foundation for building systems that interact with sensors, actuators, and microcontrollers. Next, students explore digital logic and microprocessors, where they learn how to program microcontrollers, use communication protocols like SPI and I2C, and build embedded systems that control mechanical hardware. The program also covers sensors and instrumentation, which is key to collecting real-time data from a system or environment. Students learn how to select, calibrate, and interface sensors with digital systems to provide accurate feedback. In actuators and power electronics, students study how electrical energy is converted into motion through motors, servos, and motor controllers. They also learn how to manage power flow and techniques like pulse width modulation and H-bridge circuits. Finally, students take on control systems, learning how to use feedback to regulate system behavior. This includes PID control, system stability, and how to implement control algorithms in embedded software. Altogether, these topics equip students to design intelligent, responsive systems, ranging from robotic arms to autonomous drones and smart consumer devices. The third core area in mechatronics engineering is computer science and software engineering. This area provides the tools to design and implement the software that controls mechatronic systems, bringing together the hardware, electronics, and intelligent behavior. Students begin by learning programming and embedded development using languages like C, C++, and Python. They gain experience writing code that interacts directly with hardware, reading sensor inputs, controlling actuators, and managing real-time responses. They are also introduced to software engineering principles such as modular design, object-oriented programming, version control, and debugging. These are essential for building complex, reliable systems like autonomous robots or automated machinery. In algorithms and data structures, students learn to write efficient software, handling data, optimizing system performance, and solving problems like pathfinding or real-time decision-making in robotics. Courses also cover control algorithms and real-time systems. Students implement control logic like PID controllers or Kalman filters on embedded systems, ensuring that their code responds accurately and within strict timing constraints. Communication is another key focus. Students learn to implement communication protocols and networking, such as SPI, I2C, Bluetooth, or Wi-Fi, to connect components within a system, or remotely control devices through the cloud or IoT frameworks. Finally, students explore artificial intelligence and machine learning, integrating advanced decision-making into mechatronic systems. This includes training systems to recognize patterns, adapt to their environment, and operate autonomously using tools like computer vision or reinforcement learning. Together, these skills allow students to design intelligent, connected systems from smart devices to autonomous robots. The fourth core area in mechatronics engineering is mechatronics integration. This is where everything comes together. So students learn how to combine mechanical components, electronics, and software into a complete intelligent system. A major focus is on embedded systems and real-time computing. Students program microcontrollers like Arduino or STM32 to control sensors and actuators, and they work with real-time operating systems to ensure fast, predictable system responses. In sensors, actuators, and control systems, students integrate data from devices like IMUs, LIDAR, or temperature sensors, and use that information to control motors or pneumatics using feedback controllers like PID or more advanced methods. Hardware-software co-design is another key area. Students design interfaces that allow electronics and software to work seamlessly together, sometimes using FPGAs or DSPs to accelerate processing. The program also explores robotics, automation, and industrial IoT. Students apply tools like computer vision, motion planning, and wireless protocols to build smart, autonomous systems for manufacturing or connected devices. Finally, in mechatronics system prototyping and testing, students bring their designs to life using 3D printing, PCB design, and simulation tools to build and validate their systems, ensuring they're reliable and ready for real-world use. This integration work is at the heart of what makes mechatronics unique, blending hardware and software into systems that think, sense, and act. In the upper years of the mechatronics engineering program, students move beyond the fundamentals and begin working on more advanced interdisciplinary challenges. These courses and projects bring together everything they've learned, mechanical design, electronics, software, and control to tackle real-world problems using emerging technologies. Students gain experience designing intelligent systems that can move, sense, and make decisions in real time. This includes technologies used in autonomous vehicles, collaborative robotics, wearable health devices, and smart manufacturing systems. There's also a focus on integrating artificial intelligence, ensuring secure and reliable operation in networked environments, and optimizing embedded systems for energy efficiency. The goal at this stage is to prepare students to innovate in fast-moving fields, whether that's building safer human-robot interactions on the factory floor and enabling smart automation, or contributing to the development of next-generation medical and biohybrid systems. These advanced topics allow students to deepen their expertise, explore areas of personal interest, and position themselves for impactful careers in research, industry, or entrepreneurship. While the mechatronics engineering program does not offer formal specializations, students do have the opportunity to customize their degree by pursuing an option, which is a focused set of courses in a particular area of interest. Options are open to students across the Faculty of Engineering and typically involve completing 5 to 8 courses. Some of the most popular choices for mechatronics students includes artificial intelligence, computing, and software engineering, as these align closely with the digital intelligence systems focus of the program. However, there are 13 options in total, covering a wide range of fields from biomechanics and environmental engineering to entrepreneurship, quantum engineering, and management sciences. Choosing an option is entirely optional, but it can be a great way to explore a secondary interest or align your degree with a specific career goal in emerging tech, business, or interdisciplinary areas. Just like in all of our engineering programs, students in mechatronics engineering at Waterloo participate in our paid co-op work program throughout their degree. Over the course of 6 work terms, students gain up to 2 years of paid work experience, applying their skills in real-world settings while building strong industry connections. Mechatronics students work in a wide range of roles, which span software, hardware, robotics, automation, control systems, and even product management. These roles often involve developing intelligent systems, designing embedded hardware, writing control software, or supporting full development or full product development cycles. The variety of co-op jobs reflects the interdisciplinary nature of the program and gives students the flexibility to explore different career paths, whether it be in startups, large tech companies, research labs, or advanced manufacturing. These work terms provide more than just exposure. They build practical skills that align directly with career goals and often lead to full-time job offers after graduation. It's one of the key ways that Waterloo Engineering helps students graduate with both a degree and real competitive experience. This slide shows the two co-op streams for Mechatronics Engineering, Stream 4 on the top and Stream 8 on the bottom. Both streams lead to the same degree, include the same courses, and complete 6 paid co-op work terms. The difference is simply when those work terms happen. In Stream 4, students start co-op earlier with their first work term in the winter of their first year. This stream alternates between study and work terms fairly quickly and is a good fit for students who are excited to enter the workplace as soon as possible. In Stream 8, students complete 2 academic terms before their first co-op, which begins in the spring of first year. This gives a bit more time to build technical foundations before applying for jobs. Stream 8 also includes an 8-month co-op term in fourth year, allowing students to take on larger projects and gain deeper experience with one employer. If you receive an offer of admission to mechatronics engineering, you'll have the option to complete a form to indicate your preferred stream. While we'll take this into account when assigning streams, you're not guaranteed to be placed in your preferred stream. Both stream options offer strong employment outcomes, and employers are very familiar with both schedules. No matter which stream you're in, you'll graduate with extensive hands-on experience and strong industry connections. Graduates of mechatronics engineering are prepared for a wide range of careers thanks to their multidisciplinary training. The roles listed here highlight just how versatile this degree is, whether you're designing automation systems, developing robotics software, building embedded devices, or working in cutting-edge areas like AI, IoT, or biomedical technology. These career paths span multiple industries, including automotive, aerospace, robotics, consumer electronics, and healthcare. This means you're not limited to one sector. Mechatronics engineers are in demand anywhere technology is advancing. For students interested in further specialization or research, many graduates choose to pursue graduate studies through programs like a Master of Engineering, Master of Applied Science, or even a PhD. These advanced degrees open doors to roles in research, academia, and highly specialized engineering fields. That brings us to the end of the session. Thanks so much for watching. If you have more questions, don't worry, there are a few great ways to follow up and get the information that you need. If you'd like to hear directly from current students, check out our Ask a Warrior chat platform. You can connect with real Waterloo engineering students to ask about academics, co-op, residence, student life, whatever's on your mind. For admissions-related questions like requirements, timelines, or the application process, feel free to reach out to our admissions team at enginfo@uwaterloo.ca. And if you're thinking about visiting campus or joining one of our events, head over to our tours and events page to see what's coming up, whether that's in person or virtual. Thanks again for tuning in, and we hope to see you at Waterloo Engineering.